Hello everyone, I am Yildirim from University of Trento, and in this presentation I'm going to show our recent work on defragmenting energy storage in batteryless sensing devices, and this is a joint work with my PhD student Yildiz from Ege University. And who we are doing research on embedded systems, and definitely we enjoy playing with batteryless devices, and the main motivation of our work is coming from this research paper, which is talking about a federated energy storage architecture for tiny batteryless devices. And one of the limitations of the proposed architecture is the peripheral starvation problem, which we are dealing with in the context of this work. So definitely we are considering transiently powered computers. We have a lot of emerging platforms nowadays like Kamarotera, Flickr and Wispcam, and all these devices are microcontroller based devices that operate by harvesting energy from ambient energy sources. So definitely this energy should be stored somewhere else. So we have two types of energy storage architectures. One is like the centralized energy storage architecture where we have a kind of single central capacitor. This capacitor powers all of the peripherals in the system. That means like definitely one of those peripherals might drain the energy stored in this capacitor very quickly. And also, since we need to provide energy to all of these components, we should have a big size capacitor, and definitely we fix the operating voltage to a kind of fixed value, but definitely we have peripherals that can operate at different voltage values, voltage ranges. So if we fix that voltage range, that means like we might increase the energy consumption of the peripherals also. So considering those disadvantages, we have like the federated storage architecture where we have a kind of distributed set of capacitors. Each capacitor is dedicated to one of the peripherals. Okay, so we have a first stage capacitor which is charged directly by the energy harvester, and thereafter, after the first stage capacitor is charged, the next capacitor, let's say, will be charged, and then after it is like charged, the next capacitor will be charged, and this continues according to priorities of these capacitors. So this leads to shorter charging times because now we, let's say, distribute the capacitors, and also since each sensor, each peripheral has its own capacitor, that means like we can adjust the operating voltage range of these sensors. That means like rather than having a kind of centralized range, we can have definitely dedicated ranges which reduces the energy consumption of the peripherals. So considering this architecture, we realize that it has a kind of energy fragmentation problem. That means like when we look at the architecture, we might see like some capacitors are like almost being depleted, some of them can be half full, for instance. But if we somehow defragment this energy, we might have a kind of, for example, full capacitor that might provide energy to one of the peripherals in the architecture. So literally, even though the total energy in the system is sufficient to let some tasks, let's say, execute, with this architecture we are unable to do that. Okay, so definitely we need a kind of architecture that overcomes this problem. So this is what we are proposing in this work. We propose GRANT, energy defragmenter, and energy storage architecture for tiny embedded devices. So the GRANT defragments available energy in the federated architecture. Okay, that means like we have distributed capacitors definitely, and the our architecture GRANT has energy transfer unit and charge level controllers, and energy transfer unit is used to transfer energy among the capacitors, and also energy transfer unit provides dynamic prioritization of capacitor charging. Okay, these are the features that are enabled by E2, and charge level controllers are used to receive, to understand the charge level information of the individual capacitors. Okay, with these two basic components, energy defragmenter, GRANT defragments the available energy in the federated energy storage architecture. So we have the critical questions like how will the energy be transferred between the capacitors. So this is the main feature of GRANT. So we have like, we might have different capacitor sizes. These capacitors might have different energy levels. For example, if we would like to transfer energy from a kind of high energy capacitor to a low level energy capacitor, is it like feasible? So also, for example, there might be cases like both capacitors might have equal energy levels. So is it feasible to transfer energy from like among the capacitors that have the same energy levels? And also, what is the energy transfer efficiency? All these are the critical questions that we are going to answer shortly. So the first question is like, how can energy be transferred? So this is a critical question, and we might have, for example, an RC circuit. So a capacitor, a resistor, and another capacitor. We can close the switch and we can let the current flow from capacitor 1 to capacitor 2. So with this circuitry, we observe like by LT-SPICE simulation, like when the energy level of these capacitors reach to an equal voltage level, the energy transfer stops. So definitely 50% of the total 50% of the total energy is also lost due to the resistor here, and also the energy transfer stops when these capacitors like reach to the same voltage value, which is like not a good option for us. So another strategy is like, let's use an LC circuitry. So we have an inductor. That means like energy is converted, for example, in this capacitor. If we close the switch, the energy in this capacitor will be converted into a magnetic field energy on this inductor. Okay, so that with this circuitry, energy transfer from high voltage to low voltage capacitor is enabled, but the the reverse transfer. Let's say if this capacitor has a kind of high value, but if this capacitor has a kind of low value, I cannot transfer energy from low capacitor to the high energy capacitor. So let's observe the operation of this circuitry. I close the switch. If this capacitor has a kind of high voltage, definitely the inductor stores the energy, and then this stored energy in this inductor, let's say, starts charging this capacitor. Since the current passing through the inductor cannot be changed instantaneously, so this capacitor is completely discharged, and then at this point capacitor C2 is charged, and thereafter, since the switch is not closed, a reverse current occurs, and then this capacitor starts charging C1. So there is a kind of oscillation, which we don't want. We want to stop transfer, right? So another option, like let's use a diode here, so that it prevents the reverse current. But when we place a diode here and when we close the circuitry, due to the threshold voltage of the diode, definitely not the whole energy in this capacitor will be transferred to C2, but also the thing is like we cannot transfer energy from C2 to C1. There is no two-way energy transfer in this circuitry. Okay, if we look at the simulation results, we see like definitely not all of the energy of this capacitor can be transferred to C2, because like there is a kind of energy threshold introduced by the diode, and also as you see, like I cannot transfer energy from C2 to C1. So considering these like drawbacks, and also when we look, the energy transfer efficiency is like almost 64% in LT-SPICE simulations, we propose another circuitry, a novel circuitry according to us, like as you see in this figure. So we have two switches. I mean, when I would like to transfer energy from C1 to C2, what I do, I close S1, and then the energy of this capacitor is stored in this inductor, okay? And then when all of the energy is stored in this inductor, I open that switch, and then I close S2, so that the inductor starts charging C2. And when C2 is completely charged, we open the switch. So this circuitry also enables energy transfer between C2 and C1 also. If I would like to, let's say, charge C1 from C2, what I need to do is like I need to close S2 so that C2 charges L1, and then I open S2 and I close S1 so that L1 charges C1, and then I open S1. So we have like two-way energy transfer. And using our LT-SPICE simulations, we see like almost all the energy in capacitor 1 is transferred to capacitor 2 in the first case, and we see like there's a kind of 97% energy transfer efficiency. So this is a kind of nice circuitry that we want for sure. And based on this circuitry, we propose, an energy transfer unit in our ground architecture, one of the main components. And it is a kind of switching circuit that enables and controls the energy transfer in every direction. So in the center, we have an inductor, and we have like A and B ports, and that inductor has two switches, this one and this one. With these switches I can select like which port of the inductor will be connected to the ground, so that I can control the energy transfer direction. And for each peripheral I have definitely, in our architecture, each peripheral has its own capacitor, and each capacitor has also two dedicated switches. One switch is used to connect the capacitor to the A port of the inductor, and another switch is used to connect the capacitor to the B port of the inductor. So by managing these switches like in accordingly, that means like we can definitely select, for example, energy transfer between these and these, and definitely the flow of energy will be realized in accordance with the how to say closed switches in this architecture. So we have two switches per each storage capacitor and two switches for the inductor, for just the centralized inductor, and this circuitry definitely enables any kind of energy transfer among any kind of capacitors. So one thing to mention is like we have also A2 control software, and this software definitely manages these switches, and in order to control these switches we have a kind of software layer, and this software layer is used to play with the switches to, let's say, adjust energy transfer at runtime. Okay, so apart from energy transfer unit, we have charge level controllers, because the energy transfer unit should know the current energy status of the capacitors in order to decide like which capacitor I can use to get its energy to charge another capacitor. So we need to keep track of the energy status of the capacitors. So per peripheral or per capacitor we have like a digitally controlled potentiometer and two capacitors. And the thing is like with these not capacitors, comparators. With these three comparators we can detect three voltage signals. Like one is like the lower threshold signal, which indicates that the capacitor is empty, and another is like upper threshold signal, which indicates like the capacitor has sufficient energy to power the peripheral. And we have a kind of maximum charge level signal that indicates like the capacitor is full. So for example, when the maximum level charge level signal is triggered with this circuitry, the microcontroller or the control software can understand that, okay, this capacitor is full, let's charge the next capacitor. So all these decisions can be done at runtime by the software thanks to these circuitries. So considering these basic circuitries, we performed simulations in order to understand like what is the energy efficiency of this architecture, and like, okay, we have several scenarios. For example, we can transfer energy from a capacitor to another one when they have equal energy, or when one is low, another is high energy level, and also vice versa. And also, for example, what happens when I want to transfer energy among the capacitors between different sizes. So for this we set up that simulation scenario. We assume like we have three peripherals, we have those capacitor values, and in the center we have that inductor that has a kind of 56 millihenry value, and we set like maximum voltage, upper threshold and lower threshold signal values to those values during our simulations. So let's take a look. Initially, in the thing is like the parameter. The priorities, the charging priorities we selected was like first barometer, then leaf wetness, and then the transceiver. So first the barometer is being charged to 2.7 volts, and then after that leaf wetness is being charged, and thereafter we start charging the radio CC 1101. Okay. So this is like the initial operation, initial scenario. Thereafter, we try to explore the simulation, the case like when the two capacitors have equal voltage. So for this, we wanted to transfer energy from barometer to leaf wetness sensor. Here, as we see, like these two capacitors have the same voltage, both are at 1.7 volts. And what we do is like we use the energy in the barometer, okay, and we charge the leaf wetness, and it happens. We see like we are successful. And thereafter, the second scenario is like we wanted to transfer energy from a low voltage capacitor to a high voltage capacitor. It's quite different, right? I mean, we first wanted to charge the barometer, okay, in scenario, as we see, like we have the barometer sensor, like we, in the first scenario, let's say since it has the higher priority, it's charged to this value, and then thereafter we wanted to charge it more using the leaf wetness sensor, and as you see, like here, the leaf wetness sensor decreases and the charge level of the barometer is increasing, which means like it is now 2.14 volts at this point, okay. And thereafter we used the transceiver, the energy in the transceiver, which is like shown here, okay, to charge the barometer sensor more. So as we see, like we let the barometer sensor to reach 2.5 volts, and with this scenario we observe like low energy capacitor to high energy capacitor energy transfer is feasible. And the last scenario, which should be 3, not 2, right here, we observed like if it is possible to transfer energy from high energy capacitor to low energy capacitor, and here like we wanted to transfer energy to from leaf wetness sensor to the transceiver. So as we see, we have the transceiver here, and we have the leaf wetness sensor here at 2.7 volts, and we definitely get all the energy and charge the radio capacitor to that value from 1.94 volts to 2.61 volts, and we see like this is definitely feasible. So in all these scenarios, definitely we see like the energy transfer efficiency of our system is between 94% to 97%, and which is like quite good news based on our simulations. So one question that might appear is like, okay, these energy transfer scenarios are nice, but someone else definitely should open and close those switching circuitry, let's say, at appropriate times, right? The energy transfer efficiency is dependent on the timings, on and off timings of these switches, which has been done by the A2 software, okay? So how these values are calculated, how these switches are like opened and closed, please check our paper for the details. The necessary formulation is presented in our paper. So as a conclusion, during this presentation, I presented you a novel energy storage architecture for tiny batteryless devices, which we call GRANT, Energy Defragmenter. It combines the benefits of centralized and federated energy storage architectures. It can defragment the available energy in the federated capacitors, and based on our simulations we saw like 94 to 97% energy transfer is feasible among the capacitors. So definitely during our simulations we try to use the most realistic values of the components of these components that we have selected, okay, by using the data sheets and websites. But definitely, in order to show the real benefit of GRANT, we need a real-world implementation, which we leave it as a kind of future work. So in order to understand, like, if the complexity and the additional components introduced by the GRANT architecture, the software layer, the energy transfer unit, and the charge level controllers, I mean, do they really make sense? We are not able to understand this reality by looking at only the simulations. We need to have a real-world implementation of GRANT to understand the real benefits of this architecture. So thank you very much for listening to me, and this is at the end of my presentation, and definitely please do not hesitate to contact me for your questions. Thank you and see you.